Pluto, a distant and mysterious planet, was once a member of the planetary family in our solar system. However, recent alarming statements made by well-known astrophysicists like Michio Kaku and Neil deGrasse Tyson have brought Pluto back into the public eye. They have made a shocking discovery. Neptune and Pluto could potentially come into collision. But how could this happen, and what would happen if it did? Is this a unique cosmic phenomenon, or is there more to this upcoming cosmic impact than meets the eye? Come along with us as we investigate the possibility of a Pluto-Neptune collision. The scientific community is still captivated by Pluto, which was once classified as a planet, but was later reclassified as a dwarf planet due to its peculiar orbit. Leading scientists have recently discovered that Pluto's path is dangerously close to Neptune's orbit. Famous astrophysicists like Neil deGrasse Tyson and Michio Kaku are raising concerns about the likelihood of a devastating collision between these two celestial bodies, a scenario that has the potential to be a serious threat to Earth. But how could something like this happen? Pluto's orbit around the Sun is very unusual compared to that of any other planet in our solar system. A single orbit takes a remarkable 248 years to complete. Pluto's lack of a complete orbit since its discovery in 1930 adds to its mystique. However, Pluto's orbit is not simply slow. It is also extremely elliptical, which sets it apart from the more circular orbits of larger planets. The fact that Pluto's orbit is skewed 17 degrees from the plane of the solar system only adds to the complexity of the situation. Its path is much more extreme than that of the other planets because of this inclination, adding layers of complexity to its movement. Pluto's interaction with Neptune's orbit is one of the most intriguing aspects of its orbit. Contrary to what we might anticipate based on the relative positions of the planets in our solar system, Pluto comes closer to the Sun than Neptune does for about 20 years of each orbit. Naturally, this raises the question of why Pluto and Neptune have not collided. The answer lies in the gravitational pull of other planets and celestial bodies. Shortly after Pluto's discovery, research into its orbit began. Its strange path bewildered early astronomers. Pluto's orbit stood out because of its steep tilt and elliptical shape, in contrast to those of other planets whose orbits are somewhat aligned with the ecliptic plane. The discovery that Pluto's orbit crosses that of Neptune sparked a lot of scientific interest. The remarkable property of space mechanics is the stability of Pluto's orbit despite these irregularities. When looking at how Pluto, Neptune, and the Sun move, the so-called three-body problem comes into play. Understanding how three celestial objects move and interact with one another through gravitational forces is required to solve this problem. It is difficult to predict their paths, which is why terms like scope libration, VZK wobbling, and IML vibration become important. When Pluto crosses Neptune's orbit, it stays at least 90 degrees away from Neptune, preventing their paths from colliding. This is referred to as an IML vibration. The vertical movement of a celestial body in its orbit is referred to as scope libration. This means that Pluto is above the plane of their orbits when it is closest to Neptune or any other large planet, providing additional protection from potential collisions. The VZK wobbling, named after the scientists VZ and K, who investigated how space objects interact with gravitational forces, is another important factor. Pluto's apparent erratic behavior is explained by this phenomenon, which describes how the gravitational pulls of Pluto, Neptune, and the Sun interact with one another to maintain Pluto's path stability. Despite the fact that Pluto's orbit appears to be erratic, this wobbling mechanism contributes to the planet's steady motion over extended time scales. Pluto's orbit is stabilized by these intricate forces, which prevent it from colliding with Neptune or deviating wildly. Understanding how orbits change as a result of the gravitational pull of multiple objects necessitates an understanding of the three-body problem. We can learn more about Pluto, our solar system, and even distant celestial bodies and their stars by studying this. In the late 1980s, mathematical simulations showed that Pluto's orbit is still chaotic, despite having these stabilizing factors. Over the course of millions of years, even minute variations in its starting conditions could result in significant variations. However, Pluto's orbit is stable over extremely long time scales, effectively limiting any potential disruption despite the inherent chaos. New insights into how the gravitational effects of giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit have been provided by recent computer models. The unique relationship between Pluto and Neptune is demonstrated by these models. Neptune completes 3 orbits for every 2 that Pluto completes around the Sun. Pluto's orbit is stabilized by this connection. However, Neptune is not the only driving force. Both Jupiter's and Saturn's gravity contribute to the system's stability. These simulations show that Pluto will remain in a stable orbit for billions of years, thanks to Jupiter's gravitational pull alone. Pluto's safe course is maintained by Neptune, Jupiter, and Saturn working together to prevent any catastrophic collisions or other disruptions. Without these gravitational forces, the solar system would be much more chaotic, with planets and dwarf planets like Pluto potentially colliding with one another or being ejected from their orbits. To get a better understanding of the dynamic nature of our solar system, it is essential to comprehend Pluto's orbit. The case of Pluto is a great illustration of how the intricate interaction of gravitational forces can bring stability to even the most seemingly unstable orbits. It also emphasizes the significance of ongoing investigation and observation for gaining a deeper comprehension of our place in the universe. The unpredictability of celestial mechanics is demonstrated by the investigation of Pluto and its orbit. Pluto's case clearly demonstrates the concept of orbital chaos, which refers to the extreme sensitivity of a body's orbit to its initial conditions. Over time, Pluto's orbit could be significantly altered by even the smallest adjustments to its speed or position. Researchers have gained a better understanding of Pluto's motion through the use of simulations. These computer models make use of intricate mathematics to simulate the gravitational interactions between Pluto and other celestial bodies. Astronomers are able to observe how even minute adjustments can profoundly alter Pluto's long-term orbit. These simulations revealed something fascinating about Pluto's orbit in the late 1980s. It might be stabilized by IML vibration and scope libration, but it might still be erratic. Over extended time spans, even minute variations in Pluto's initial position or velocity can result in significant orbital shifts. However, Pluto's orbit has remained relatively stable over billions of years, despite the apparent chaos. This demonstrates that despite the fact that its path may appear chaotic, it actually follows a pattern. We are reminded of how much is still unknown by Pluto's orbit. The larger dynamics of the solar system can be better comprehended by gaining an understanding of the gravitational interactions that occur between Pluto and giant planets. It demonstrates the effects that each planet's location can have. Profound effects that have an impact on the stability and course of other bodies in the system. So why now, after all these years, are astrophysicists raising concerns about a possible collision between Pluto and Neptune? An insightful perspective is provided by Neil deGrasse Tyson, a leading astrophysicist who helped popularize the study of cosmology. Tyson, who is known for advocating that Pluto be reclassified as a dwarf planet, is of the opinion that this change is a reflection of our ever-increasing comprehension of the solar system. He views Pluto's reclassification as an advancement in our understanding of the numerous bodies that orbit our Sun, rather than a demotion. The foundation of Tyson's approach to celestial mechanics is ongoing education. He believes that the erratic orbit of Pluto is an indication of how much more there is to learn about space. Scientists and the general public alike continue to be captivated by the fascination with unknowns, such as the possibility of catastrophic events occurring between Pluto and Neptune. Tyson acknowledges that anything from a close flyby to a catastrophic collision remains possible, and his predictions for the future of Pluto take into account its highly irregular orbit. Another well-known physicist, Michio Kaku, joins the chorus of experts who worry about Pluto's long-term future. Theoretical physicist Kaku investigates the mathematical basis for the potential interactions between Pluto and Neptune. According to his theories, Pluto's orbit appears to be stable at the moment, but its future remains uncertain. He warns that even small changes in the gravitational forces that exist between Pluto, Neptune, and other planets could result in a catastrophic event over time. Despite Pluto's current stability, Kaku's predictions highlight the orbit's vulnerability. It is essential to consider the future of Pluto's orbit as we continue to investigate the workings of cosmic mechanisms. The unpredictability of celestial dynamics means that we can never completely rule out the possibility of a collision with Neptune, despite the fact that current models indicate that such a collision is unlikely to occur anytime soon. Pluto's orbit will continue to be shaped by interactions with other celestial bodies, and even the Sun's gradual transformation into a red giant and eventual collapse into a white dwarf could change the solar system's gravitational landscape, potentially affecting Pluto's orbit. Even though it seems unlikely that Pluto and Neptune will collide anytime soon, anything is possible due to the inherent uncertainty of predicting celestial dynamics over such vast timescales. The forces at work in orbital mechanics are powerful and intricate, and even the smallest change can accumulate over billions of years and have the potential to alter the orbits of distant objects significantly. We are brought back to a fundamental principle by this uncertainty in space exploration. As we learn more about the universe, we become more aware of how much is still unknown. Our comprehension of planetary orbits, gravitational interactions, and the fundamental laws that govern the cosmos continues to be challenged by the study of Pluto and other distant objects in our solar system. New information may either support or refute our current theories as scientists continue to observe Pluto and Neptune. Although the possibility of a catastrophic collision between Pluto and Neptune may appear remote, it serves as a reminder of the unsolved mysteries of space. The possibility of a collision or near miss between Pluto and Neptune remains a compelling illustration of the complexity and unpredictability of our solar system, even as our space exploration tools provide us with more precise methods to simulate, predict, and observe these cosmic phenomena. It is unknown whether such an event will ever occur, but it demonstrates the dynamic nature of our cosmic environment. We are compelled to look beyond our current understanding and embrace the mystery of space by the narrative of Pluto's orbit. It forces us to reconsider our perspective on the universe and to remain open to the unexpected. We are reminded that we have only scratched the surface of what the universe has to offer as scientists continue to unravel its mysteries. The question of whether Pluto and Neptune will continue to orbit safely or encounter a cosmic collision in the future remains unanswered and will only be clarified with the passage of time and subsequent discoveries. The story of Pluto's orbit serves as a metaphor for the mysteries that continue to intrigue and excite scientists as we advance our understanding of the cosmos. Despite the fact that a collision between Pluto and Neptune is unlikely in the near future, it serves as a reminder of how little we know about the vastness of space. In the ever-expanding field of astrophysics, these celestial events, regardless of how unlikely they may appear, invite us to continue pondering how the universe functions and the fundamental forces at work. There is constantly more to learn. The tools and techniques used to study distant worlds like Pluto are getting better as we get deeper into space. Exploration. Researchers are able to track these celestial bodies with an unprecedented level of precision thanks to advanced telescopes, space missions, and more advanced computer simulations. The mechanics of planetary motion, gravitational interactions, and the long-term stability of our solar system are better understood thanks to these advancements. The ongoing advancement of observational technologies is one of the most exciting developments in the investigation of Pluto and its orbit. New space missions are launched on a regular basis with the intention of examining distant solar system objects. These missions, like the New Horizons spacecraft, have given us valuable information about Pluto and other worlds in the Kuiper Belt, giving us a better understanding of their characteristics. We gain a deeper comprehension of these far-off bodies and the mechanisms that control their movement with each new discovery. Even after Pluto was reclassified as a dwarf planet, the fact that it continues to be a source of fascination and research demonstrates the ongoing fascination with this faraway planet. Although the scientific community no longer considers Pluto a planet, it continues to hold a significant place in the public imagination. The definition of a planet, the complexity of our solar system, and the ways in which our understanding of space is constantly evolving have all been the subject of debate since its reclassification. The ever-evolving state of scientific knowledge is brought home to us by this ongoing investigation of Pluto's path. As new data and theories are proposed, what we know today may change tomorrow. It is impossible to completely rule out the possibility of Pluto and Neptune colliding in the future. However, it also illustrates the larger theme of space's unpredictability. Because of the universe's very nature, we can only make predictions with some degree of certainty, and even the most meticulously constructed models can be supplemented by new findings. The desire to comprehend the fundamental workings of the universe is the driving force behind the pursuit of knowledge in astrophysics. Scientists are not only gaining a deeper comprehension of how gravitational forces shape the motion of all celestial bodies by studying Pluto and its relationship with Neptune, but they are also gaining an understanding of the particular dynamics of these two planets. These studies' findings have far-reaching implications not only for our solar system, but also for a more comprehensive comprehension of planetary systems across the galaxy. Additionally, the significance of scientific community collaboration is brought to light by the investigation of Pluto's orbit. The analysis of Pluto's movements is made possible by the contributions of astronomers, physicists, mathematicians, and astrophysicists, each of whom has a distinct perspective on the issue. As a result of this collaboration, more refined models of planetary motion and a deeper comprehension of the delicate equilibrium that maintains harmony throughout the solar system have been developed. Even though a collision between Pluto and Neptune may appear remote, it serves as a useful reminder of the ongoing difficulties we face in predicting the behavior of distant universe objects. Anything can occur due to the chaotic nature of celestial orbits, and our comprehension of the universe will continue to develop as additional data are collected.